Hi, my name is Yasamin Borhani from Toosi University of Technology, and I'm here to explain the simulation of controlling flexible joint to our manipulator as my Mechatronics project. Nowadays, the robotic arms are among the most popular machines used today for many tasks. They can be used independently or they can be part of the bigger robots. As you can see in the picture, our manipulator has two revolute joints and three solid components. A flexible joint is a coupling which can transmit torque between two shafts which are not aligned. In the robotic problems, these may be caused by gearboxes or motor shafts. These are the base of my project and we will come back to them later. So let's get started. At first, we have to create an environment to design the project. So we click on the Simulink tab. After that, here in the Simscape option, we can find multibody and it provides us some of the necessary blocks which are going to be used in this project. Okay, a robot consists of links and joints, but before defining them, we need to establish a base of the robot. The solid block which you can see it here is what we need. If we double click on that, you can see it has many options like shape and dimensions. You can choose the predefined shapes like cylindrical shape, sphere, brick, etc. And there is another option here. If you design your component in the other softwares like SolidWorks or CATIA, you can upload it here. For my project, brick is fine. After that, we can change the dimensions value, and here we can choose the unit we need. Centimeters is good for my project, and as you can see, there are three numbers here which represent the length of robot in the X, Y, and Z axis. After that, here we can choose the inertia parameters of component, and we can choose it based on density or mass. If we know about material of component, we can choose density, and if we know the value of the mass, we can choose mass. I prefer to choose density because the solid blocks are made of aluminum, so I changed the value of density to 2700. And I think it's done. If you want, you can change the color of your component here, but I think it is not really necessary. After that, as you can see in the picture, the robot consists of two links, and for defining them, we can use solid block. And we can change the dimensions here. The first arm is 2 meters, so we can change the unit here. There is an interesting point, and it says that if you press F5, you can see the changes you have made. Here, the component is updated. For defining the second link, we do the same. It is 1.5 meters. For connecting these components together, we need revolute joints. If you search it, you can find it easily. And we need two revolute joints. The first one is between the base and the first arm, and the second one is between the first arm and the second arm. As you can see, the revolute joint has two ports, base frame and follower frame. And we connect it to the right components. And we have to connect the world frame to the base. Each component should have one frame, and if I run it, you can see why. Here, if you see it carefully, it seems something is going wrong, and all the components are connected at the gravity of mass point. So it is not correct, and we have to move components in order to put them in the right positions. There is another problem. As you can see, the z-axis is not in the right position, and it should be perpendicular to the page because we are using revolute joints, and we should change it, and as you can see, it is not true. If you click on the toggle visibility of frames, you can see the component frames. Okay, for solving this problem, rigid transform block has been defined. And if you double click on that, you can see it has two options, rotational transform and translational transformation. So, at the first place, we choose the standard axis, and along x-axis, we rotate the frame about 90 degrees. And we put it here. And we put another one for visualize it correctly. And we need a transformation about z-axis too, and the offset should be the half of the length of the first arm, so 1 meter. As you can see here, our problem, it seems to be solved, but the base and the first arm are in the right positions. And we have to do the same for the rest of our components. Here I put rigid transform blocks in order to correct the position of our components, and I put one frame on the end effector to follow the position of it in the future. In this part, the model of the robot has been defined. I added another block here. The transform sensor can measure the end effector's position along X, Y, and Z axis. These are two workspace blocks, and they can transfer data to the workspace in order to save and plot them. In this part, I'm going to design the circuit of the actuators. In fact, this part will connect the controller and the robot together. It means that at first, the controller sends the signals to the circuit, then the circuit can provide the torque in order to move the arm. So at first I bring a DC motor component, and you can choose an appropriate DC motor by reading catalogs or datasheets. So if you double click on that, you can see there is 3 options here for entering your suitable parameters. I choose by stall torque and no load speed. And these are my selected DC motor parameters. Because I want to control the torque of the motor, the controlled current source would be necessary for my project, because by controlling current we can control the torque. And for measuring the current, a current sensor is put. So we connect them together, and as you know, every circuit needs to have a reference, so electrical reference is connected here. Now is time to bring the necessary components in order to connect them to the shaft. So at first, the mechanical rotational reference is connected. Then, as I want to study the effects of the flexibility of the shaft, a flexible shaft component would be necessary. If you double click on that, you can see you can change the parameters here. I changed the stiffness value to 0.1. And you can change the units here, but I didn't change them. The other component that we need is gearbox. And because DC motor can't provide high torque and they have high speed, using gearbox can be helpful, because by using gearbox we can decrease the speed and increase the torque. And here we can define the gear ratio. I choose 300. And we can add rotational friction, because it can add the damping value to the motor. Here we can get our output now, but if we connect 2 sides of the output to the ideal torque sensor, the torque of the motor can be measured. That torque will affect the robot motion, but we need to define the effect of the robot motion on the motor too. We will do this by defining a constraint. It means that for each motor and joint, the speed of the motor shaft should be limited to the speed of the robot joints. For applying this constraint, we take the angular speed of the joint as the input of the angular speed sensor. Here is the ideal angular velocity sensor. In other words, this sensor provides the interactions between the robot and the motor. So we connected here. We should connect the speed of the joints here in ideal angular velocity source, and here we get the torque, and we connect the torque sensor to the robot's model. Now the question is, how can we connect the torque to the robot's model, and how can we measure the joint's speed? If we come back here and double click on joint, we can see there are 2 options here, actuation, and sensing. Here we can choose torque provided by input, and if we click on that, we can provide torque as an input. And by sensing, we can choose position and velocity. And so you can see here we can connect the torque as an input, and we can measure the position and the velocity here, and we can do the same for the second joint. As you can see here, I defined the torques as the input and the velocity and the position as the outputs. Here we can put the circuit in the subsystem and name it as motor 1. We want two of them because we have two joints, and in the next step we have to connect these blocks together. As you can see here, the related ports are connected together. For review, we have two motors because we have two joints, and there's a point here. If we want to plot the physical signals like current signal, we can't connect it to the scope directly. And here there is a block named physical to simulink converter, and it should be used for connecting the physical signals to the scope. And we can use simulink to physical converter when we want to connect the unitless signal to the controlled current source, for example. So in this part, we designed the actuators circuit and we connect it to the robot model. In this part, I'm going to briefly explain what the trajectory is and then design it. In control systems, usually there is a set point or a trajectory as a reference, which we expect the output of the plant to follow that. There are several methods for designing the required trajectories for a robot, and these trajectories can be described in different workspaces. It is out of the scope of this project to discuss all of them in details. So here we will design a cubic polynomial trajectory in the joint space. Each joint requires its own trajectory. In this case, we have two joints, so we should design two trajectories. Trajectory is simply a function of time, which tells us at each time step what should be the angular position of the joint. This trajectory should have some specifications. For example, at the start, the joint position is at the initial position and the velocity is 0. At the target point, the velocity is also 0 because we want the robot to stay at that position. The derivative of the trajectory with respect to the time determines the velocity of the joints. So four conditions to be satisfied are: at the time t equals to 0, the position should be the initial position of the joint. At the time t equals to 0, the velocity should be 0. At the time t equals to final t, the angular position should be equal to the target value, and at the time t equals to final t, the velocity should be 0. By using these four constraints, the coefficients of the polynomial can be found. Now it's time to design the trajectories. For designing them, I use MATLAB functions. And this is the equation of the cubic trajectory, and it gets time, initial position, final position, and final time as the inputs. As you can see, the clock is connected to the time, and the initial position and the final position are defined here. So we expect from robot to start from initial position and reach the final position in 20 seconds. For designing the trajectory for second joint, we do the same and define the initial position and the final position and the time duration, and it is done. So in this part, we designed the trajectory, and in the next part, we are going to design controllers. In the last part, the controllers will be designed. At first, I'm going to calculate the error of the joint's position, and as we know about trajectory, it provides us the desired position at each step. And as I activated the positional sensors, and I can get the position of each joint at each time step from here. So I bring the add block, and I'm going to calculate the difference between the trajectory and the position of the joint. Here, as you can see, I can't connect the signal to the add block because it is a physical signal, and I should put the physical to Simulink block here, and then I can connect this signal to the add block. So it's the first error here, and we do the same for the second error. Now we can connect the errors to the controllers. Here we use PID controllers because PID controllers are model-free controllers, and I don't have to calculate the dynamics of the robot, and by choosing the appropriate coefficients, I can control the robot. Now we need a scope for plotting the error of each error. We want 2 ports, so we define it. And we do the same for the second. Before running the project, there is a point that we should consider. Here the final t is equal to 20, so we should change the simulation time to 20. Now we can run it. As you can see, it creates an animation and it seems that it is working well. We can study the plots later. Here, as you can see, the blue plot is the trajectory and the yellow one belongs to position of joints. And it seems that the yellow one is following the blue one, and we can see the plot of errors too. This plot belongs to second joint, and it seems that our controller is working well. So we add a scope for plotting the errors, and for transforming the unit we add a gain block here. We want to plot it with degree unit. And we do the same for the second joint. Now we have to run it again in order to see the errors plot. As you can see here, the maximum error is between 1 degree and 1.2 degrees, and for the second joint, maximum error is between 1 degrees and 1.5 degrees, and it is good for our project. Here you can check out my coefficients PID controller, and by experience I think these are good parameters for controlling this project. And these are for second joints. So this project is done. Thanks so much for watching.